I welcome you to the class of econometric methods. This is a continuation of a previous class on lag variables. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, AMU. In our previous class, we had seen that what is the importance of lagged variables? Like they are basically a very inherent phenomenon in economics, be it consumption, be it investment, in all these things. Like in consumption, your today's consumption depends upon not only on today's income but also on the income which you have been gaining in the previous years or previous months, and likewise. Then we had also seen, like in investment function also we have discussed this similar things. Now then we discussed the lags, the reason for these lags, psychological reasons, technological reasons, and institutional reasons. We had then next moved to the ad hoc estimation and the issues associated with ad hoc estimation. Like you are seeing that when you are trying to estimate with the same data, when we had taken one lag, fine. When we had taken second lag also, it shows the theoretically a positive relationship which can be justified by theory. But when we incorporated another lag, the third period lag, then we found that the variable, it became negative. So something which should have a positive sign, and in two lags it was showing a positive sign in the previous time when it was taken a lag of 1. But next time it turns out to be negative. This indicates that there are issues, there can be issues there can be issues in estimation related to multicollinearity. Also, the other issue is of because the more lagged variables you add, the more degrees of freedom we are losing, and we cannot have much liberty with the years of data which we are having, particularly in economics. Then we differentiated between two type of models. One is the one in which simply the independent variable is present as in the lagged format, like xt, xt minus 1, xt minus 2. Then we move to another type of model wherein the dependent variable yt is present as an explanatory variable yt minus 1. So then after that we have moved to the various lag structures which we can have. We can have a declining one, then a rectangular one where all the weights are given the same. In the declining one, the weights are declining, and in the inverted, that is the weights are first increasing, then decreasing. So we have seen these things. We discussed, then we have prominently discussed the Allman's distributed lag scheme. Moving on, then we have gone through the Cox geometric lag scheme. This is what we have studied in our previous lectures. Today's discussion is on Nirlov's partial adjustment model. This is basically a theory based on behavioral hypothesis. See, the stock adjustment principle implies a particular behavioral pattern. Here it is assumed that there is a desired level of capital stock which an entrepreneur thinks is the right for the smooth production process without any excess capacity or any overworking of the existing machinery and all those things. But because of the gestation period involved in all investment projects, the actually realized change in the capital stock in any one period is only a fraction of the desired change. In other words, the adjustment of a capital to the desired level is only gradual due to the technological, financial, and administrative and say managerial constraints. So herein we have an yt asterisk, that is the desired level of y in any period t. It depends upon the value of x in that period xt. So Now this is what we refer to the stock adjustment principle, and we follow this model. Yt asterisk is equal to b naught plus b1 x1 plus u. But the issue over here is that this Yt asterisk, it cannot be directly measured. It is not observable. This is what an entrepreneur thinks is the best Yt for him, is the best, say, the best level of output for him. But this is not which can be directly seen or directly observed. So we postulate a gradual change, and that is it postulates that the actual change in capital stock in any given period time t is some fraction gamma of the desired change of that period. If this gamma is equal to 1, we have Yt minus 1, and this is my desired level minus Yt minus 1 plus the error term Vt. If the value of this gamma is equal to 1, it means that the actual stock of capital is equal to the desired stock. That is, actual stock adjusts to the desired stock instantaneously in the same period t. But if this gamma is, say, it is equal to 0, it means that nothing changes, since actual stock at time t is the same as the observed in the previous time period. But typically this gamma is expected to lie between these two extremes, since adjustment to the desired stock of capital is likely to be incomplete because of rigidity, inertia, contractual obligations, and that is why we say there is a partial adjustment going on. So here, this is gamma. So this value, it should be between 0 and 1, it should be greater than 0 and less than 1. And then what is Yt minus 1? This is the actual change in the capital stock, and Yt asterisk minus Yt minus 1 is the desired change in capital stock, something which you want and something which you get. The behavioral rule is that the realized change in the capital stock, that is Yt minus 1, is only a fraction between 0 and 1 of the desired change. So now what we do, we have this equation Yt minus 1 is equal to gamma Yt asterisk minus Yt minus 1. Now Yt asterisk we have defined in our previous case. Yt asterisk is equal to b naught plus b1 x1 plus ut. Now this value we insert over here. This value we insert in the equation, in the above equation. So what we finally get is Yt minus 1 is equal to gamma, then the value of Yt asterisk, that is b naught plus b1 x1 b1 xt plus ut minus Yt minus 1 plus Vt. This, when we open up, we put gamma inside the bracket, and open this bracket, what we get, gamma beta naught plus gamma b1 xt plus gamma ut minus gamma Yt minus 1. Then we have that Yt minus 1 plus Vt. This is by the manipulation, algebraic manipulations we get it. This what you do, we take Yt minus 1 common, and the error term, this is 1 and this is 1 error term, we combine these two, so we get the composite error term V plus gamma ut, and we have this gamma beta naught, then we have this gamma b1 xt, and this Yt and Yt, these two we combine together by taking 1 minus gamma Yt minus 1. See, once we obtain the estimate of the adjustment coefficient gamma, we can easily derive the long run function by simply dividing gamma beta naught and gamma beta 1 by gamma, and omitting the lag term, which will be giving you Yt asterisk is equal to beta naught plus beta 1 xt plus ut, which represents the long run or equilibrium demand for capital. Now, so what is this showing? This is showing that capital stock in any one period time t depends partially on the level of output in that period and partially on the existing capital stock at the beginning of the time period. See, unlike Quick, in this model, the disturbance term has no direct connection with its own previous values. It is a completely different thing. So we may assume that this new error term, that is V plus gamma ut, it is not autocorrelated. So what we have seen in the previous case in the Quick's model, we found that we are apprehensive that there can be a problem of autocorrelation, but in this formulation of Neil-Love's partial adjustment model, yt is present as an independent variable in its lag form, it's there, but the error term v plus mu gamma ut is such that we are optimistic that the problem of error autocorrelation will not be present over there. So this is what we refer to as the Neil-Love's partial adjustment model. A similar model, we move on to Kagan's adaptive expectation model. This is also in the same league of lag models. See, the Quick model which we had seen previously was an ad hoc, since it was obtained by a purely algebraic process. It was devoid of any theoretical underpinning. But this Kagan's adaptive expectation model, it fills this gap, and we look at it with a different perspective, and that is, economic agents will adapt their expectation in light of the past experience, and that in particularly they will learn from their mistakes. Say, here what we see that this is also based on behavioral hypothesis, this Kagan's adaptive expectation. We can relate with the value of y in any one period depends not only on the actual value of xt but also on the expected or permanent level of x at that time, that is xt asterisk. We will see, it is same in the like today's consumption, it depends not only on the income, on the transitory income, but what is the permanent income, things like those. Like as an example, suppose that the quantity demanded if it's a period of inflation is determined by the expected price rather than the actual price. So what we do that instead of P we take, for a quantity demanded, instead of P we take PT asterisk. That is what is the expectation of the prices, and it will determine what will be the quantity demanded. Now see, we have the Friedman's permanent income hypothesis, one of the basic hypotheses that is taught in macroeconomic classes. So therein the level of consumption is determined by the expected or permanent income yt. So we can say that Ct is equal to E1 yt asterisk plus U2. Now this expected variable or ex ante variables which are not observable. To measure such expectational models, we must find a way to substitute the expected variable, because this is not exactly, you cannot measure. This is done by postulating a specific rule for the formulation of expectations, and this is what Kagan's adaptive expectation model is all about. So we have formulated a model that yt is equal to b0 plus b1 xt asterisk plus ut. This this rule implies that expectations are adaptive, that is, the current expectations are formed by adapting or modifying previous expectations in the light of actual adjustment. That is what has happened before. I think this will again happen. In the current experience, expectations are reformulated in each period. So that is, the economic agents will adapt to their expectations in light of their past experience, and that in particular they will learn from their mistakes. More specifically, you can say that it states that the expectations are revised each period by a fraction by a fraction of the gap between the current value of the variable and its previous expected value. So what we have, xt asterisk minus xt minus 1 asterisk is equal to gamma xt minus xt asterisk minus 1, where you have this, the value of gamma is, again we take it between 0 and 1. Now here gamma, that is the expectation coefficients, imply that the elasticity of expectation is less than 1. Now again, so what we have xt asterisk minus 1 is the change in the current expectation. This change is only a fraction. This change is only a fraction gamma of the difference between the current achieved value of the variable xt and the previous expectation xt minus 1 asterisk. So the original model, yt is equal to beta naught plus b1 xt asterisk plus ut. It can be written as, if I write it in terms of b1, because we want to derive xt asterisk. So it is b1 xt asterisk is equal to minus b naught plus yt minus ut. Now this what we have, xt asterisk is equal to minus b naught by b1 plus, now what we are just writing in terms of we are taking b1 over to this side, so the entire thing is divided, that is b naught minus b naught by b1 plus 1 yt minus b1 minus ut minus b1. We get this equation. Then what we do next is we lag by one period. When we lag by one period, that is xt asterisk minus 1, this we get is minus b naught by b1. Again yt minus 1, also it gets a one period lag, ut minus 1, you get a one period lag. Now in this equation, xt and xt minus 1, xt asterisk and xt asterisk minus 1, we have got all the derivation for this. We insert the values. We insert the values here, and for xt minus 1 we insert the values here. So now what we get, again xt is as it is, and again xt asterisk minus 1, we insert the values over here. So minus b naught by b1 plus 1 by b1 yt minus ut by b1 plus b naught by b1 minus yt minus 1 by b1 plus ut minus 1 by b1 is equal to, now what we are doing, we are multiplying this with gamma, so we have gamma xt. Now then gamma, again these entire thing, minus b naught by b1 minus gamma 1 minus b1 yt minus 1 plus gamma 1 by b1 ut minus 1 gamma. So this is the derivation which we get upon further manipulation. In the sense, we are writing this equation in terms of yt divided by b1, and all other terms we take it to this side of the equation, to the right hand side. Upon doing that, we get this final equation, that is 1 upon b1 yt is equal to minus b naught by b1 minus b naught by b1. One term will be plus. This is already one term, it should be plus. When this goes, it becomes minus, this goes, it becomes plus. So one of them is plus ut by b1 plus gamma xt plus gamma b naught by b1 plus gamma yt minus 1 divided by b1 plus 1 by b1 yt minus 1 plus minus 1 by b1 ut minus 1 by b1, there is a plus sign is missing over here, 1 by b1 gamma ut minus 1. So in all the terms except for this one, except for the term gamma xt, in all the terms what we are having b1 in the denominator. So what we do, in order to get rid of all of it, we multiply the both right hand side and the left hand side by b1. So what we get is yt is equal to ut, in this and this is cancelling, so you have ut minus yt minus 1 minus yt minus ut minus 1. Now here this b1 is in the above because there was nothing to cancel out in the numerator, plus gamma b naught minus gamma yt minus 1 plus gamma u t minus 1. This we can we are rearranging the terms. So finally what we get is yt is equal to gamma b1 xt plus gamma b naught plus 1 minus gamma yt minus 1 plus ut minus 1 minus gamma ut minus 1. So this is what is the final equation which we are getting. So basically what we have done, when we are doing this, we are arriving at the same expression which contains the same variable as the Cox model and as the Nirlov's partial adjustment model. All the three assume the same lag scheme, that is declining geometric pattern for lag coefficient. However, its error term suffers from the same defect. This error term, it suffers from the same defect as the error term of Cox, because again there can be a problem of autocorrelation, but nevertheless it provides a fairly simple means of modeling expectation in economic theory by postulating a mode of behavior upon the part of economic agents which seems eminently sensible. So now we discuss the case of, with this we bring an end to our discussion on lagged variables. Thank you.